Hi everyone, and welcome back to Physics 4A. Today we're going to go ahead and talk about angular momentum. So the first idea we want to understand is rolling motion, and that's going to be a combination of rotational and translational motion. And specifically we're going to look at rolling motion without slipping. Okay, and to analyze that we're going to need some linear variables of velocity and acceleration of the center of mass of the wheel in terms of angular variables that describe the wheel's motion. Okay, so we're going to go ahead and look at this figure here, starting with part A here. And we just want to notice that there are force vectors involved in preventing the wheel from slipping. So we have a normal force, we have a static frictional force, okay, and of course the force due to gravity and the force of the motion pushing it forward. Okay, so all of these forces that are on the wheel combined prevent the wheel from slipping. Okay, now in point B here, or part B, we want to notice that P touches the surface and is at rest relative to the surface, okay? But as the ball rolls, that point will have some velocity relative to the center of mass, okay? And that velocity is negative r omega I hat. Okay, so if we say that this is the x and y axes, the positive x, y axes, okay, the point is moving in the negative I hat direction. Okay, now we can also say that the velocity of P with respect to the surface is the velocity of P with respect to the center of mass plus the velocity with respect to the surface. Okay, so this might be an easier way to put it. So the velocity of point P with respect to the surface is equal to the velocity of P with respect to the center of mass plus the velocity with respect to the surface. And this velocity is the center of mass velocity. Okay. Now, since the velocity of P relative to the surface is 0, like we said up here in part B, okay, that means that the velocity of the center of mass is equal to r omega. Okay. All right, so now we can find the linear acceleration. Okay, now from the previous equation we found that V center of mass is equal to r omega. Now we'll take the derivative to find the acceleration. Okay, so this is going to now be the angular acceleration here is equal to d omega dt, okay? And so we find that A center of mass is equal to r alpha. Okay, so we are basically saying because this is true, we can go ahead and take that derivative of this part here, okay? Pull the r out since it's a constant, and we get this, okay? Then we can also find the distance here to the center of mass, and that is going to be equal to r times theta. Okay, or I'm sorry, this is going to be the distance traveled, or the displacement. Okay, so this is going to be equal to the amount of angle that this wheel has covered. So it's rolling in this direction, right? And so as it rolls, it's going to say hit this point right here, and then it'll hit point B over here, okay? And so whatever this angle is that it covers times r will be that displacement or that distance, okay? All right. Now looking at rolling motion with slipping, there's another figure here. Looking at part A, we have kinetic friction, that's this guy here, and it arises between the wheel and the surface because the wheel is slipping. So now we have a kinetic friction, not just a static friction, okay? And when the wheel is rolling and slipping, you see here, the relationships between the linear and angular variables are not valid anymore. So there needs to be something else to relate these guys up here, okay? So these are no longer valid. Okay, so let's look at an example. So this is 11.2, and I'm going to try my best to keep the problems simple. I don't think we need to go into too much detail here, okay? So this is the figure that is along with this problem. It states a solid cylinder rolls down an inclined plane from rest and undergoes slipping. It has mass m and radius r. What is its linear acceleration? Okay. So what we can do is we can apply what we have in the past, looking at free body diagrams, and determine this acceleration of motion. Okay, so we have that it's going to be moving in the x direction, right? That we can tell since it starts at rest at the top here and then is moving down, and this is in the positive x direction. Okay, so we'll just focus on this x unless we have to bring in the y coordinates. Okay, so we have the sum of forces is going to equal mass times acceleration of the center of mass, and that'll equal mg sine theta, and that's an I hat, okay, minus f sub k I hat. Okay, and since we don't have any values, we can solve in terms of all of the other forces or variables. Okay, so we have the linear acceleration is then equal to g sine theta minus f sub k over m. And that should be the I hat direction. That should be your linear acceleration. Now we could go further and talk about what our frictional force is, F sub k. Remember that F sub k, or our force, is going to be some constant mu times our normal force, okay? And our normal force in this case, this should be in the x direction. If we're looking at F sub y, that will be n sub j minus mg cosine theta j hat. And because it's only accelerating in the x direction here, it's going to be equal to 0. Whoops. 0. Come on. 0. Okay. Therefore, n is equal to mg cosine theta. So f sub k is going to equal some mu mg cosine theta. Okay, so our acceleration is going to equal g times sine theta minus, plugging that in, we have a mu. The m's will cancel. I pulled out the g times cosine theta. And we should put a k down here for kinetic energy. I'm sorry, the kinetic friction. And then I hat. So this should be your full answer here. Okay. Now, if we're looking for B, it states what is its angular acceleration about an axis through the center of mass. So this one is going to be a little more involved, and I am going to have to get another page. Yeah. So let me do that, and I'll be right back. Okay, so with that, let's go for part B. Now, I needed to write down a couple of equations. So this first one, we have to now turn Newton's second law, into in terms of torque. So remember that Newton's second law states F is equal to mass times acceleration. Okay, so we're essentially doing the same thing, but now just in terms of torque. Okay, so we have the sum of the torque of center of mass is equal to I center of mass, or inertia, times angular acceleration. Okay, and so our torque is going to be our frictional force, F sub k, times R, and then our inertia here, our center mass of inertia, is going to be 1/2 mr squared. Okay? And that is from, I believe, our previous chapter. Okay, where they had that big chart of all of the different inertias. And since we just are looking at a disk, this is what we are looking at. Okay, so now we can go ahead and use this to solve for alpha. So we've got alpha is equal to, and we'll move over the 2 sub fk r and divide over mr squared. And so we get F sub k r mr squared. Now we can plug in our F sub k. Since we did have it back here, that's going to be mu sub k mg cosine. So we have, oops, I meant to cross one of those out. Put a 2 there. Okay, so 2, we had mu sub k mg cosine theta over mr. So our mass cancels and we get 2 mu sub k g cosine theta over r. And so that is our angular acceleration for this problem. Okay? All right. So I just wanted to quickly mention the conservation of mechanical energy in rolling motion. Okay, notice the similarities here. So we have E sub t is equal to 1/2 mv center mass squared plus 1/2 I center mass omega squared plus mgh. Okay, so these two are your kinetic energy, and this last one is your potential. Okay, so just notice the similarities. Really all that's going to change is we have this other term here for your kinetic energy. Okay, and so this takes care of your rotational motion. Okay. All right, so I'm going to stop the video here, and we will continue on looking at the next example, 11.3, in the next video.